Okay, good afternoon, everybody.
Good afternoon.
Good afternoon. Um, okay. So, are there any questions regarding the homework assignment, the first homework assignment with the cycles? The deadline, I think, is Tuesday next week, if I'm right. Huh? I got a no. 36, 37 now participants in the Zoom. Or this Friday. I don't remember. Was it this Friday or? You're right. I think it's this Friday is the deadline. And today you get a new homework assignment, which deadline is in 2 weeks again. So I've received already some of the homework assignments. I also received some of the questions. On the homework assignment, it says that please submit the homework assignment via email to my email address. Yes, Friday night, or if you submit it at midnight, it's also okay. Leave it up to you. So by sometime on Friday, please send it to me via email, and then I will start looking at the assignments. Okay. And today you get another homework assignment which is related to the 3D design, which I also mentioned last time already. We will have another homework assignment. Um, then I would suggest that we continue with the lectures. And the last time I discussed some of the things related to design parameters, but I didn't finish, so I would like to finish this today, because it turns out that with the Zoom I'm much slower than in a real classroom setting, um, which I think would also make much more sense if we just record these lectures and then put them online instead of still having live Zoom sessions. I'm not sure what you think about it, but I think live Zoom is not as effective and efficient as basically in a real classroom, or also having them just pre-recorded snippets of topics recorded and then uploaded on YouTube. And then we could basically meet just for discussing these topics. But anyway, Sig Klein and I decided to make it like this with Zoom. And so then I would like to discuss, or continue. I will just go quickly through the part that we already discussed last Friday, which are the design parameters and the performance characteristics. So I've changed the slides slightly. You will find them, of course, online on Brightspace, but also on the Google Drive that SIG clients and set up. You will find the slides, and the first part I will just go through quickly because it's already something we discussed last time. But I would like to finish this today uh, because it's a quite important topic also. And so I said that basically we have three design parameters, right? The first one was the flow coefficient, which you can see here, which is basically defined as the axle velocity through the machine divided by the blade speed. And of course, where you define the blade speed is left open here, so you can decide what kind of U you actually take, right? If the mid-span radius is not constant at R is not constant, then of course you have to choose a U or blade speed in order to define this. And also CX, if it's not constant, which one do you take? But let's say for mean design and for mean line analysis, these are the flow coefficients, and then they are easy to define. So we said the flow coefficient, we said the loading factor was the second parameter that is very important, which is defined as the um, change of total enthalpy divided by the velocity squared, so by the blade speed squared. And we know that for delta H0, we can also use the Euler equation, which is nothing else than delta of U times C theta. And that was the Euler equation. And then we had the third one, which was the degree of reaction. So we have three parameters: flow coefficient, loading factor, and the degree of reaction. Last time I also asked you a question related to the degree of reaction, where I asked you, for example, what happens for degree of reaction equals 0. And if you assume that there are no losses, will the pressure stay constant, the velocities be the same, and so on and so forth. So this is something that it's easy to understand, and it's a very important parameter also, because they all three are equally important, but this is the last one, degree of reaction, which basically determines how much of acceleration or deceleration you have in the rotor with respect to the total stage, right? If you have no acceleration in the rotor of a turbine, then the degree of reaction is 0. And we use this design parameters, and then I use the Euler equation. I use simple trigonometric functions in order to come up with an equation which basically expresses the loading factor, which is this one here, and the degree of reaction simply as a function of two angles. And these are the angles that I have chosen to design that stage, right? These are the angles that are independent of the mass flow, and they're independent also of the rotational speed. And that's why I always said these angles for a turbine, for example, these are alpha 2 and alpha 3 in an ideal setting, right? If I have an ideal setting, I say that no matter what kind of mass flow I will push through the stage here, right? The mass flow will be probably determined by the magnitude of this velocity. Is the mass flow this one here, or is it, let's say, the inlet velocity like that, or is the inlet velocity much larger mass flow? Then I can say that the angle at the outlet of the stator, this one here, will be unaffected. It will not change, right? On the other hand, if I change the velocity of the rotor, so the rotational speed of the rotor, which is this guy here, right? This has a certain velocity u, then probably this angle also will be unaffected. This angle here, the flow angle, will not be affected by the rotational speed. And then if I continue through the rotor and I hope that the flow will follow the rotor blade, the rotor geometry, then I know that the outflow velocity of the rotor will also be this one here. And so this one also will stay constant, independent of how fast my rotor is rotating or how much mass flow I have, right? This might just become shorter, like this maybe, if the mass flow is very small, or larger if the mass flow is very large, but the angle will not change. And that's why I was able to, or that's why I wanted to express the loading factor and the degree of reaction as a function of these two angles, alpha 2 and beta 3. And so when I did that, you can see this is now for the turbine stage, very important, right? It's, there's a different equation for the compressor stage, but for the turbine stage, I get such an expression that looks like that. Then I go and use this expression, for example, and build some kind of performance map, but a performance map for an ideal situation. Let's say there's no viscosity, and no viscosity basically means there are no boundary layers, there is no flow separation, and so on and so forth. And if I have that, then I can use this equation, and I can put my psi here, which is the loading factor psi, as a function of my flow coefficient phi, right? This is phi here, flow coefficient phi. So I have psi as a function of flow coefficient phi. And so if I have a turbine like I had before, let's go back again. Let's say this angle here, alpha 2, is 45 degree, right? Alpha 2 is 45 degree, specified here. And I can see that, let's say, let's assume that my beta 3 in this case would be also 45, but keep in mind, minus 45 degree, right? Because I said that in the direction of the rotation, all the angles are positive. Against the direction of the rotation, the angles are negative. Just like for the velocity, right? This is a positive u velocity here, and this is a positive angle. This is a negative angle. So if you say that you have designed a stage where alpha 2 is 45 and beta 2 is minus 4, beta 3 is minus 45, then of course what will this be? 1 minus 1, and you get a flow coefficient that basically is 2, 5, right? Because this one, if alpha is 45 degree, and this one is minus 45 degree, then this is tangents of 45 is 1, this is minus 1, minus 1 is plus 2, and so I get an equation for the flow coefficient in an ideal setting, which is now very a linear function of my flow coefficient 1 minus, sorry, minus 1 plus 2 phi. Okay. So then is this, oops, then this is the line here. And of course, I can just say that what happens if phi is equals 0, then I will start at minus 1 here. But then if my flow coefficient increases, I will at some point reach this point here, which we called the um, uh, runaway condition, right? Where the power is equal 0 or the loading factor is equal 0 for a turbine. But then let's say if I further increase the mass flow, or let's say decrease the rotational speed, I go into this direction, into the right side of this part, and then I will get a curve that is like that, right? So this is nothing else than minus plus 2 pi. And this will be basically from here to here will be whatever, it will be, power will be positive, right? That I can extract from this turbine. And we also discussed this, and I asked you a question in one of the first lectures about velocity triangles, is what happens if the rotational speed of a turbine increases? Does the power go down or up? And you can see it here clearly now what happens. If the rotational speed increases, U increases, phi decreases, and the power goes down. So, logic. Now, for compressors, we discussed it. We didn't discuss it last time, and that's why I have to repeat it. Or that's why I was repeating the first part here, and now I continue with this lecture, which I couldn't finish last time. But for compressors, or maybe I started actually discussing it. So for compressors, we have a different equation for the loading factor and also for the degree of reaction. You can easily derive them yourself, right? It's not something that you would need to remember. You can derive it, but I think if you need to use these equations for, anyway, the exam question is an open book, most likely. You need to ask Sike Klein about that, but most likely the exam will be an open book exam, since we cannot check if you're using the books at home or not, or you can use any documents for the exam probably. So you don't need to derive them anymore. You can just simply look them up, but be aware that these equations are actually different for the compressor and for the turbine. And so again, for the compressor, what did we say here? Of course, the inlet velocity of the compressor will be completely unaffected by, sorry, not the inlet velocity, but the angle of the inlet velocity in absolute frame of reference, which is my C velocity, right, C1, will be unaffected by the rotational speed. This is U now because we have the rotor here. And it will be unaffected also by the mass flow. So if you have chosen an angle, of course, the mass flow will just increase or decrease the magnitude of that vector. And the rotational speed will not change the angle as well. So the angles that stay constant for a compressor are alpha 1. And if you continue and you hope that the flow will follow the blade geometry, then you can see that beta 2, which is this velocity here, right? This angle between the velocity of W2 and the axis, which is this one here, also will remain unaffected. So what I want to do now for the loading factor and the degree of reaction is I want to express C and R as a function of alpha 1 and beta 2, right? I have designed it, and I know that this is at my design condition. I get this C and I get this degree of reaction if I know it, if I know the angles, or the other way around. If I want to choose, if I know the loading factor and the degree of reaction, I can easily calculate what the angle should be. There's a one-to-one relationship between these two, right? And then you can see again here the equation, and if you assume that, I don't know, yeah, we can say that alpha 1 is 0, right? Then this guy will be 0, and then you have minus tangents beta 2, and beta 2 is negative. So you will get a line that actually will start at 1, but then have a negative slope and go this way, right? And so what does this tell you now? So for mass flow equals 0, you get let's say theoretically, of course, the flow will not be able to do so, the flow through a compressor. But let's say if I have a certain mass flow, so Cx has a finite value of, let's say, non-dimensional value of 1 or something, but my rotational speed u is very high, then of course what will my loading flow coefficient will be close to 0, okay? So this is increasing u. So you can see that my theoretical performance map for a compressor is the higher the rotational speed, it's the opposite of the turbine. The higher the rotational speed, the higher the flow coefficient, the higher the pressure ratio I can get out from a compressor. I feed certain amount of work into the rotor, or I provide a certain amount of work to the flow by using the rotor of the compressor, right? Then you will see that the maximum theoretical performance in this case is if I have a very fast rotational speed or the mass flow goes to 0. But of course, you know that this will not be possible to do in reality. And this way is just the opposite. And so then I also said already, mentioned some things that this is the ideal performance map of a compressor. But in reality, as I said already, you have things that can happen with the flow, which is like you can choke the flow, for example, or you can, for the compressor, you will be also able to get a surge condition. And surge condition is when the pressure ratio of the compressor is so high that the flow is not possible to go into one direction anymore, but actually we start turning around. And that's what I want to discuss now in this case. And so that's why we have discussed now the performance maps, the ideal performance maps. You're just using one simple mean line analysis, let's say, of velocity triangles at of a certain stage, compressor or turbine. And if you do so, we get the ideal performance map. But in reality, we will have to do something like measure performance maps, for example, right? We can measure them, or we can calculate them with CFD simulations. And that's why we should think of it in a different way, slightly different way. There's a one-to-one relation, of course, but similarity analysis also for turbines and compressors are based on non-dimensional analysis, right? So if you have a compressor and the compressor has a certain size, operates with a certain fluid, you would like to know how do you need to change this compressor if the fluid is changing and you would still like to get the same pressure ratio, right? Then you do similarity analysis. And the similarity analysis or non-dimensional analysis is, of course, based on deforming non-dimensional groups. And this is also something I quickly discussed already last time. So what we want basically is that we would like to have on this side here up C, right? This is the loading factor, which is the important one. We want to replace the C with, I don't know, with the power that we need for a compressor or that we get out from a turbine, or delta H 0 for the total stagnation change, enthalpy change, or also the efficiency. In reality, of course, we always have losses, and so we have limited efficiencies. And we would like to get these as a function of, I don't know, rotational speed maybe, mass flow, and other things, right? So maybe you can see it here. What is the viscosity of the fluid? What is the diameter of the machine? What is the density, viscosity, and speed of sound? And also gamma, of course, the specific heat ratio are a function of the fluid. And I didn't discuss this in too much detail, but when you see this here, you saw that I was able, let me show you this part here. I was able to create a non-dimensional relation now where we can say, okay, instead of using the flow coefficient, which is this one here, which was our performance parameter, right? Or design parameter phi here, which is Cx, let's call this one Cx, divided by the rotational speed of the rotor, is in fact also, that's what I wanted to have, a function of the mass flow non-dimensional mass flow here and the rotational speed n. Or, of course, they are equivalent, right? They're equivalent to Cx, and this guy is equivalent to U. Clear? I have the flow coefficient now as a function of non-dimensional mass flow, this part here, and a non-dimensional rotational speed. And the same for the loading factor. I have the loading factor here, C, now as a function of non-dimensional mass flow and non-dimensional rotational speed. But as you saw before, I was able to basically define a pressure ratio now, which is very important for the performance map. I will have a pressure ratio, again, as a function of these two parameters, mass flow and rotational speed, U. Or in this case, it's simply N. Right, so let's say this will be Cx and this is U. But you can see here one thing, that this in industry actually is most of the time compressors and turbines are characterized by so-called reduced properties, and these reduced properties are not non-dimensional anymore. You can see it here again. What happened is this is a non-dimensional parameter for the mass flow, but since you can read this text here, for machines with a single gas, for example, gamma can be dropped. So if you want to compare machines that always operate with air, and this is what happened in reality, is that most of these machines actually compressed air, or they used the flue gas in turbines to expand this flue gas, and then the gamma is constant. You can compare different machines among each other if they always use the same gas. So gamma can be dropped, and that's why gamma is dropped, for example, here, and also here. On the other hand, the Reynolds number can be dropped as well, because most of the time for these large machines, let's say in power plants, the bulk flow, right? So if you have a channel or something like that, then most of the time, basically, the flow will be turbulent anyway. And then you will have a velocity profile which might look like that. If you enter a duct flow, for example, and this is the velocity U, the Reynolds number determines how thick the boundary layers will be. And the boundary layer basically thickness is this part here. And so since these machines are very big and the flow velocities are quite large, it means that the boundary layers are very thin. So you can safely assume that, let's say, 98% of the flow going through a turbo machine here, if this machine is large enough, will be just the bulk flow far away from walls, okay? And then you can assume that the Reynolds number maybe also doesn't play such a large, such an important role, which is not always true, of course. You need to know about that. But in this case, you can say that the boundary layers are very thin compared to the bulk flow, which is this here. And then it has become customary in industry, at least, to further drop D and R. This one here, this is the diameter of the machine, and R, which is the gas constant, right? And so if you drop R, the diameter here, then you will see that you will end up with these equations here. Then you have a mass flow multiplied with square root of T01, so the total stagnation temperature divided by the stagnation pressure. This is the mass flow, and then you have a rotational speed, which is n divided by the square root of the stagnation temperature. It's not non-dimensional, but usually the performance map that you will find from industry have these parameters, the reduced properties, on their axis. Okay, you will see it now. But if you want to do a scaling analysis between different machines, you of course need to use this equation. Okay, this is important. So if you say that you would like to have a machine with a 1 meter diameter, or let's say you have a machine and you know about them, you know everything about this machine. You know its diameter is 1 meter. You know it has a certain rotational speed, and because of that, it will reach a certain pressure ratio. Now you can say, okay, what happens if I make this machine half the size, if I reduce the diameter by a factor of 2, but I still would like to keep the same pressure ratio, then you would be able to calculate how you would need to change the rotational speed by using simply these equations. Scaling analysis, right? You can scale different machines if you use these equations, which are the non-dimensional parameters in this case. And this is what is used in industry. You cannot use this as a scaling. You can use this as a scaling if the fluid stays the same and the sizes stay the same, but otherwise you can't. Okay. And so you can see that how does this now work if you have these new parameters and you would like to come up with a turbine map or a compressor map. Then the first thing that we need to discuss for turbine, and has been discussed and mentioned also already in one of the previous classes, is that turbines are most of the times choked, right? They're choked. So you have here the combustion chamber. Let's say here you have a flame sitting here and then it burns, and then you have the combustion chamber that goes into this turbine here, and then you have the hot flue gas entering this turbine. And you can safely assume that the velocity in the combustion chamber is relatively small, so the kinetic energy can be neglected. Then you can say that you know T01, or I don't know, T02 in this case, I don't know, and you know P0, right? You know the total conditions, the total pressure, and the total temperature. Let's say in the combustion chamber, you know how high the temperature will go, and the pressure is given by the compressor, for example. Of course, you will have pressure losses that maybe will change it, and you also have maybe some non-negligible effect of kinetic energy. But most of the time, the combustion chambers are quite big, so that the flow velocity inside the combustion chamber determining the kinetic energy is so much smaller than the enthalpy. Enthalpy is usually much higher than the kinetic energy. Because, yes. Then what happens here is you can easily derive this equation, which is called the flow capacity equation. I show it on the next slide. I will not go through it, but I will leave it in the slide so that you can check on how this equation has been derived. It's not difficult. You just need to use basic thermodynamic laws. Basically, you don't need to use gas dynamic knowledge even. You can derive this with thermodynamic equations. And isentropic relations, definition of Mach number you need to know, for example. And then you can easily derive the mass flow and the mass flow here, which is the flow capacity, okay? And as you can see on this equation, that again, let's say if kappa is always the same, because you're only dealing with air, for example, then this whole part will be just a number, right? Because what is in there is kappa or my gamma, which is 1.4, let's say, for a compressor, but if I have air, or this guy here is 287 joule per kilogram and Kelvin. And then you will see that this is just a constant, right? Of course, it depends on the fluid, but if I always deal with the same fluid, it's just a constant here. And then you can see that the mass flow is determined simply by the throat area, which is this one here. This is the throat area, the smallest area, A, usually called A star, and by the total pressure at the inlet of the turbine. So this part here, P0, which is this one, and T0. Okay. So this equation basically tells you a few things, that no matter what the pressure at the outlet is, P2, if the pressure at the outlet is small enough to reach supersonic flow at the throat, then lowering the pressure will not increase the mass flow anymore. Obvious. That I think you have heard also about this in thermodynamic in the first year bachelor. I also discussed this. After a certain pressure, If you further decrease it, the mass flow will not increase because there's no P2 in this equation, right? But you need to reach choke conditions. So, which means that if you if you have a well-defined pressure in the combustion chamber given by the compressor, if you add the right amount of fuel in the combustion chamber, you can control the temperature. And by controlling these two parameters, you basically control the whole mass flow through the gas turbine. Is controlled by this area here. Okay, and that's why the first stage of the turbine, and we discussed also steam turbines, the Curtis wheel, for example, is choked, or any gas turbine, for example, the first stage after the combustion chamber, most of the time is choked to control the mass flow, which means that independent of the exit pressure of the turbine, the mass flow will stay constant. And you can see that, of course, the higher the pressure, the higher the area, the larger the mass flow. The higher the pressure, the higher the mass flow. Of course, if you have a higher pressure, most of the time you will have also higher density. The higher density going through this choked area means you have a larger mass flow. But on the other hand, the temperature is inversely proportional to the mass flow, which means that the lower the temperature, the larger the mass flow. This also makes sense that if you have a lower temperature, it means that the density most likely will go up. If the density goes up again, you will have a larger amount of mass that you can push through this choked area. Okay? And so the choked area means basically that the flow velocity is the same as the speed of sound. And the speed of sound can be defined by also simple thermodynamic relations. You just need the mass conservation equation and the energy conservation equation. And then the speed of sound usually is defined as the partial derivative of pressure with respect to density, but we know that pressure, density, and all these other parameters always depend on two thermodynamic properties for simple substance, which means we need to define here this partial derivative in terms of keeping something else constant, right? And a pressure wave in air usually travels isentropically. There's no loss connected to it. Not completely correct, but a very good assumption. So the speed of sound is nothing else than how does the pressure change with respect to density along an isentrope, because there's no loss when a pressure wave travels through space. And that's the speed of sound definition. And depending on the gas, you can calculate this. So all of this stuff is now again given here. So I have discussed the flow capacity here. And I have derived the flow capacity on this slide, and you can see that at the end you will get this equation. I will not do it now in detail, but you just need to follow these steps, which are most of them are basically known already. This is an isentropic relation. This is also the isentropic relation basically for this definition of total entropy simply. Equation of state P is O equal RT, and speed of sound is this guy here. So for an ideal gas, speed of sound is nothing else than kappa RT, or also kappa P over rho, right? So the Mach number is speed of sound divided velocity divided by speed of sound, and if you do that, you will get this flow capacity equation. I will show you now one example on how such a thing might look like, for example, and it's a very special case. Okay, now before I show you this case, I will show now how does such a performance map for turbine look like, and this is what you encounter in industry. You have here the reduced mass flow, right? We said it, mass flow, square root of temperature divided by the pressure is this one here. This is the reduced mass flow on the x-axis. And we said that we most of the time would like to look at the pressure ratio. And so you can see already here, if my P01 is kept constant, right? It's given by the conditions of the combustion chamber, then you can see that my pressure ratio can increase by of course, if I decrease the pressure at the exit of the turbine, P2 decreasing, then this will go up. But after a certain P2, I will not be able to, so you can see that if P1 is kept constant, but P2 is decreasing, you see that the mass flow will increase. Up to a certain point, when P2 is small enough to reach sonic conditions, and then the nozzle will be choked, and then you will get constant mass flow. Even if the pressure, even if you further decrease the pressure, the mass flow will not increase anymore, right? Remember in the ideal case, in the ideal case, I had the performance diagram. Flow coefficient was C as a function of flow capacity or flow coefficient here, and we had a thing that was like that, -1 here, and it was going up, right? The same you can see here. You can also see that this is mostly like the ideal world, right? Something like that. This will be the ideal one. But then you can see that actually, since choked condition, since I cannot press more, even if the pressure ratio increases further, I won't be able to get more mass flow through this because it's choked. And then I will get actually, instead of a straight line, I will get this line here. Okay, so this is the choked mass flow. This is a typical compressor turbine map now. And you can see also that there are several lines. There are several lines here, this one here, this one, and this one. So you can see that these are different speed lines. If the turbine operates at different speeds, right, increasing n over square root of T1, you can see that these are the different lines. Because I have here mass flow only, right, and the rotational speed is not inside here, while here I had the rotational speed as well. This was Cx divided by U. So the flow coefficient combines both parameters, the mass flow and the rotational speed. That's why I get basically one line. But if I make a function where on the x-axis I only have the mass flow, which is proportional to Cx, then of course I will get several lines, because then I get another line for this is my U1, U2, U3, U4, right? And then you call them the different speed lines. And this is how it looks like for a turbine. Okay. This is one example. I hope you can see the video and the connection is fast enough that you also see this thing moving here. So this is now a radial turbine. It's not an axial turbine, but a radial turbine. You can see that somewhere here you will have the axis, right? The rotational axis, and you can see that the rotor is turning this way. So you get a capital omega, if you will. You will get a certain rotational speed here. This would be my U, right? So this would be the rotational speed of this rotor. And you can also see that these white pieces here, this one, this is the stator. This is a stator, and it looks very weird compared to a normal machine because it is formed in a way that you can reach supersonic flows in this turbine. So you can see this is the stator, right? This one here, and also this one, these are the stators. And the flow comes in like this. You know P0 and T0 here, because the velocity is so small compared to the velocity of the rest of this turbine. And so you can see that the flow accelerates up to here. Then the flow here, this is the smallest area, right? This is the A, the cross-sectional area between these stator blades. This is A star, the minimal area, or the area at the throat. And then you reach there, you reach the velocity is the same as the speed of sound. So you get a sonic condition. And from gas dynamics or thermodynamics, we know that if we want to further accelerate the flow, we now need to have instead of contraction, an expansion here, right? First I have a contraction, I have a nozzle, and then I have a diffuser here. See the diffuser. The cross-sectional area increases, right? Smallest areas, and then you can see that here, around, let's say at this point here, I will have a speed of Mach approximately 3. So my u velocity will be approximately 3 times the speed of sound. Okay, so I have a supersonic flow in this turbine, and you can see that then because of that, you get, of course, a very large expansion in the stator, right? You have very small velocity here, or let's say stagnation conditions here, and then you accelerate the flow to 3 times the speed of sound. So the velocity vector, you can imagine, will be very long. So you have very large expansion. And in fact, this expansion in this turbine is a pressure ratio of 100, right? You can have pressure ratios of 100. And then you see that you have, here we have Mach number 3, very large velocity, supersonic flow. And supersonic flows behave in a very weird way. If you want to change the angle in a subsonic flow, you can easily change the angle by just putting a guide vane and then you change the angle. But if you want to change the flow angle in a supersonic flow, you have to do it by introducing shock waves. And I'm not sure if you can see it here. You can see the flow comes on the upper side of this stator in this direction, right? This is one flow direction. And on the other side, the flow comes this way. So now you have two flow regions that meet each other like that, right? So at some point, they cannot cross each other because you have mass conservation. At some point, once these two flows on, let's say, this side of the stator, there's no suction side or pressure side, but on this side of the stator, this is the stator trailing edge. This is called the stator trailing edge, this guy here. This guy is the stator trailing edge. It's the last part, right? And so you can see that the flow on one side has this angle, the flow on the other side has this angle, and at some point the flow should go this way. So you have to change the velocity from this one here to this guy, and from this one to this guy, which means you can only do that by creating a shock wave. And that's what you see here. You can see here shock waves. These are shock waves. So in order to change the direction of the flow in a supersonic flow, you have to introduce a shock wave, and across the shock wave, of course, you have generation of entropy, and also a large increase in pressure. And then you can see that this shock wave here will increase the pressure, and then you get also flow separation here, and so on and so forth. Okay, so this is an extreme example on a choked turbine with a pressure ratio of approximately 100. Okay. Then this is for you to read in the slides also. So this is just a summary on how a turbine performance map will look like. And now this is something I discussed already last time. So you can see here compressor performance map. Again, you have the the reduced mass flow rate on the x-axis here, the pressure ratio on the y-axis. And we have speed lines, right? So these lines are constant speed lines. And we said last time that the theoretical line would be something like that. This would be the theoretical line, the 1 minus something, right? C equals 1 minus phi times tangents alpha 1 minus tangents beta 2, and so on and so forth. And so the difference here are the losses, nicely visible here in this case. You can nicely see the difference between the ideal and the real one, because this line you have a constant speed, n is constant, or u is constant, right? And then you get this speed line, you get this speed line. If you increase the speed, if you increase the speed further, you get this line. And you can see that along the speed line, you have a limit on the upper side for the pressure ratio, which is the surge line, which means that the pressure ratio is so high that across the compressor, you can no further increase the pressure and you will get flow separation here. So the flow should go this way, or maybe the flow will at some point turn even around and go this way because the pressure here is so much higher. At the outlet is so much higher than at the inlet. And on the other hand, you can also have a lower limit here, which means that the lines will become more vertical, which you can already see here. The lines are vertical here. And then if this line becomes vertical, you get the choke condition, just like in the turbine. So this is now the choke line, and this is the surge line. And yeah, there's a lot of research still done also at universities, is to actually investigate how compressors start with the surge. And before they surge, you get compressor stall. And this just shows you, for example, what will happen if the pressure ratio is too high. You will see that this is the rotor of the compressor, and then the boundary layer will start separating. You get all of the separation here. And then this thing, where basically there's no flow going through anymore, the flow will just stagnate. So it's called stall. These plates will stall the flow. Then the flow will not go through anymore, and you will get flow maybe through these guys here. So we have a stall cell. This is called a stall cell. And these stall cells actually can rotate with a different speed than the rotor itself. So you get very strange phenomena that can happen. Direction of the stall propagation, for example, is different than the speed of the rotor. And it's very important also to predict this. And so that's why there's a lot of research in order to understand when this happens and how to prevent it also. This is basically this line here, right? We would like to increase the operating range of a compressor by trying to push this line further up so that you have a large operating range. And for that, you need to understand how this surge and stall actually can happen. And with that, I would say that we have a break again, and then I continue with the 3D design, and I will finish with the homework assignment. If you have any questions now to these topics that I discussed now, please leave them in the chat window, and then I will look at them during the break and answer them after the break. But let's have 15 minutes, or let's say let's be back at 4:45. Thank you. Okay. So there are some questions, two questions here that I would like to discuss now. The first question is that why would you want to approach such high speeds, right? There was one question. Why would you want to approach such high speeds in a turbine if you cannot make up the right angle of attack? Or is it a pure theoretical turbine? To the second question here, it's not a purely theoretical turbine. This is a CFD simulation of a turbine that actually operates in reality. And it doesn't work with steam, but it works with a different fluid, in this case, toluene. So it's a complex fluid. Basically, you can also call it an oil. You take an oil and then you boil the oil, right? So you, instead of boiling water, you boil an oil, and you get vapor. And that vapor now is expanded inside this turbine. And that vapor is toluene vapor. And that is really operating for recovering waste heat. So there's the waste heat that is at certain locations. You maybe have some waste heat from certain industry or from from greenhouses in the Netherlands, because the greenhouses they are actually powered by even small gas turbines, and the small gas turbines have a large exhaust gas or high temperature exhaust gas, and that high temperature can be still used to extract energy and to create electricity. And so this is what happens here. You get the heat in this Rankine cycle. from the waste heat of a gas turbine or diesel engine or anything else, and then you expand that vapor inside this turbine. And because it's relatively low temperatures also and small powers, you can have a very large, so instead of having several turbine stages with a different fluid, like toluene in this case, you can have in one turbine stage pressure ratios of approximately 100, right? So very, very high pressure ratios, which you cannot have with steam, or you cannot have it with air, for example. So they are very high pressure ratios in one stage. And because of that high pressure ratio, you have very high flow velocities. And because of the high flow velocities, you get shock waves. And you still get the angle of attack, which is okay. So, I mean, of course, there are large separations, but the separations are basically because of shock losses and so on and so forth. But what we did in this with this turbine is, you can see this is a simulation of the original design. And what we did is we improved that design. We reduced the shocks here, we reduced the separations, and we made the flow much nicer through this turbine. And in reality, we have also tested this turbine, and it makes actually provides a lot more power for the same heat input. This one is the initial design, which is very bad. But if you improve the design, you can get rid of the shock waves, even if it's supersonic, and you can make a very nice flow through the rotor. Okay, to answer the first question. Then another student asked a question here. Are compressor stall and surge the same? No, they are not. So you can stall inception. I think I have it here. Maybe I have here. Yeah. So compressor surge is really a complete flow reversal over a large part of the annular geometry of the compressor. Compressor stall is this part here, where only small part of the whole compressor is actually separating the flow. Okay, so stall is only there are several stages to surge. Stall inception, which makes this if you put a pressure probe here, and that's also what they do in aero engines. They try to control the mass flow, and they try to control the rotational speed in such a way that you don't get stalled. Because in the first engines, gas turbines that were propelling an aircraft, for example, you could actually see compressor surge, and then you would have the gas turbine below the wing, right? Something like that. This is the wing, and this is the gas turbine, an old one with a very low pipe pass ratio, or maybe not even a fan. Flow will come in here, and flow has to go out here, right? And so here you would have somebody combustion chamber. Here you have the compressor stages, and here you have the turbine stages. And this is the combustion chamber. And the flow is supposed to go through the compressor. The pressure is supposed to increase. Then you're supposed to burn that high pressure air with some fuel, and then you expand it in the turbine. But if you have compressor surge, what happens is that all this flame here can actually go out in the front. And so there are videos online on YouTube. You can check compressor surge at takeoff, for example, because at takeoff you get actually quite high pressure ratios and in the compressor, and then it can actually happen that the flow will completely reverse, and then instead you will get the hot gases come out in the front. Compressor surge. But before compressor surge, you get the stall, and before stall, you get stall inception. And stall inception is the first part of this, is the first stage. And the important thing is to detect this first stage. And once you detect the first stage, you can counteract. And so if you put a pressure probe here in front of this compressor, and you record the pressure, then the pressure will do something like this, right? Depending on the blade passing frequency, you would have some amplitudes here or some waves here, depending on the blade passing frequency, because compressor goes down like this. But then compressor surge can be detected by putting a pressure probe here, and then you will see that at some point, all of a sudden, the pressure will go up. Very irregular, something like that. And once you detect this one, you know that you're very close to compressor surge. and compressor stall, which can lead to surge. And most of the time, I'm not sure if you can see it here, is that the compressors, this will happen at the tip of the blade of a compressor, because this is where the loading factor is the highest. And this is what we are going to discuss now. How is the loading factor actually changing as a function of the blade height? Okay. Now let's go to this part here. Yes. So I don't have any interactive questions for you today. Just me giving a lecture, very unidirectional. So I'm talking a lot. And but if you have questions, please don't hesitate to put them in the chat window. Okay, to try to make it slightly more interactive. But now we can discuss the 3D design. So we have talked about the mean and the middle of the blade. We have been able to define the velocity triangles, the design parameters, and then we are able to discuss also how the performance changes with respect to rotational speed and mass flow. And now we can see how does it actually change across the whole blade length, right? So we have several compressor and turbine blades here. And then you can see that on very extreme example, for example, this guy here, right? The fir tree root here. This is called the fir tree. You can see this here, and now I cannot see it anymore. This is called the fir tree. And that is slid into the rotor, right? The rotor has a part like that. Like this. And that part goes in here. And then you have these blades going this way. And you can see if this is the axis here, this is the inner diameter and this is the outer diameter. And of course, on the outside, you will have a casing, and between the casing and the blade tip, you will have the tip clearance here. This is the tip clearance. And across the tip clearance, we discussed it already, you will have a flow, depending on how big the pressure differences are between the suction side and the pressure side. And but more importantly, what we want to discuss is also, of course, the blade velocity or the blade speed is simply a function of u is equals r times omega, right? So the higher the radius, the larger the blade speed. And in order to counteract the large blade speed, the blade needs to be twisted, right? Something like that. So you have a twisted blade. And how you twist that blade, you can think of, yeah, it's pretty obvious. If I have a blade speed that is a function of the radius, I need to adapt it in such a way, but that I can account for this larger blade speed at the tip. But there are some design guidelines, and this is what I want to discuss with you now. So there are some effects that you need to take into account in order to really calculate how you need to twist the blade. And when you twist the blade, you need to also, you will see how things change. In this case, for example, degree of reaction, loading factor, flow coefficient, and whatever and whatnot, right? And so this is, now I think I have here, is it prepared today? Yes. So imagine you have a stator. The flow comes in this way, right? And it will go out this way. You see that you go this way, then the flow follows this one here, and then you will get the flow that is this, right? And so I've made a plane. This is a plane, let's say. And this plane is called axial plane because it's at constant axial distance or something like that. So it's this one here. And you can look at the flow velocity in this plane. And we need to make, for this, what I'm going to discuss now, we need to make certain assumptions. So some of the assumptions that we would have is that we can say that the radial velocity, so the velocity in this radial direction, again, we can assume that it's almost zero, right? VR, the CR is almost zero. So there's no secondary flow, but there is in reality a secondary flow. which maybe I can discuss later if we have the time. But you also have boundary layers here on the hub. This is called the hub. So here you will have boundary layers. And also here you will have boundary layers on the top, on the shroud it's called. So you have boundary layers, and the boundary layers, we are also going to neglect them. So we can assume that in most of this plane here, the flow will be homogeneous, or there will be no variations of the flow inside that plane. Okay, so any derivative of the flow velocity with respect to this direction, to the theta direction, this is theta, this is the radial direction, and this is the axial direction. So any derivatives in these three directions basically are zero, right? And we also say that we don't want to take into account the boundary layers. So if we don't take into account the boundary layers, we can also say the flow has no viscosity. And then we can take the Navier-Stokes equations in cylindrical coordinates, right? And this is something that you have discussed in, maybe not in cylindrical coordinates, or maybe you did, in the advanced fluid mechanics of AFD, advanced fluid dynamics class with Daniel Tam. And so I just copied these equations basically from the Wikipedia page. Or you can derive them in Cartesian coordinates, you can derive them in cylindrical coordinates, or in Cartesian coordinates, spherical coordinates even, or any coordinates if you want to make it more complicated. But we said now that we can neglect the effects of viscosity because we are staying away from boundary layers, and we say the velocity has no gradient, then the shear is zero. So viscosity is not really playing a role. You can cross out these terms and things become already much easier. So, but I would like to see how if I can come up with a simple relation here that can describe maybe pressure gradients and velocities in this plane. Okay, and you already know what this will end up with, but I show you this in a very complicated way by using the Navier-Stokes equations. And then you can see that here also, if I assume that the flow is steady state, then all the temporal derivatives are equal zero. And you can see they're all partial derivatives, right? They have also partial derivatives here because all of these quantities inside the Navier-Stokes equations, of course, are function of more properties. And then you see here that if I assume that the radial velocity is zero, then all of these terms, for example, will be zero as well. U r, this one here, U r, the radial velocity component is already zero, so there will also not be a variation in theta direction. This will be zero. What about that guy here? This is U phi, and U phi in our terms, you called it C theta, is U phi in this equation, right? So it's a C theta. You can see here I have C theta. This is the red line here. And so a C theta squared divided by R is balanced by the pressure gradient, dP dr, which means that I need to have a pressure change in radial direction, right? And this is simple. You could have seen it already and guessed it probably, that the pressure gradient dP dr is nothing else than the circumferential velocity, and there's a rho here, not to forget this rho here, so I can put 1 over rho, is U phi, and let's write it in our terms here, C theta squared divided by R. Comes out from this equation here. I can also look at the phi equation, but you will see that everything will be zero, right? So these equations don't give me anything. The thing that I get is basically that the tangential velocity squared, C theta squared divided by R, is equals the pressure gradient in radial direction divided by rho. Okay, it's just the centrifugal force is causing an increase of pressure, if you will. And then we also had other equations. I hope I remember all of this stuff here. So we have also the enthalpy, the total enthalpy. We have been able to define it as static enthalpy plus C squared. And now I can already make the kinetic energy and split it up. I call it C theta squared, and I use Cx squared, right? This is nothing else than C squared, the kinetic energy. So what I would like to do is now I would like to establish a relationship between, let's say, how the total enthalpy is a function of the radial direction, right? So then I will be able to say something about my velocity triangles if I make certain, if I decide certain constraints, then I can come up with certain velocities also as a function of the radius. This is r, okay? So then what do I need to use? We can see that I have here a dp dr, so the pressure gradient is derivative in r. So maybe I can also use this equation and make a derivative in r, so I can say, and I do it now in a total derivative here, dr is equals dh dr plus, so I take this equation and I do, so dr, right? So I just take a derivative of this equation with respect to r. And then, of course, this guy here, derivative of c theta squared dr is nothing else than 2c theta dc theta dr. Then the 2 cancels out and I get c theta dc theta. And if you are very eager, you can also do it yourself quickly and check that I don't make any mistakes. But of course, this is pretty clear. Now you see that I have a total enthalpy, and remember in the Euler equation, I had an equation that was saying the change of total enthalpy is related to the change of the product U times C theta. It's the Euler equation. So, of course, this is something that I would like to keep, and I would like to find an expression which states something similar. So I like the total enthalpy. This one is okay. Let's say this guy is okay here. C theta and the derivative of C theta in R is also important. How do I need to change the tangential velocity? How does C theta need to change with respect to R? Or how does the axial velocity have to change with respect to R, right? This is things that I would like to keep. But you can see that I have also this here, dH dr. This is the static enthalpy. How does the static enthalpy change as a function of R? And that I would like to replace now with this equation that I have here. Because this is already C theta R here. I have C theta R, and I have the pressure gradient and the enthalpy gradient. So maybe I can use this equation somehow to replace my dH dr. And you got some ideas on how I would do that? What can I use? What other equation I can use in order to perhaps use the relation for the pressure gradient, radial pressure gradient, which is a function of C theta, in order to replace dH over dr. Any ideas what I could use? So we have used the momentum equation. The continuity equation is a pretty obvious one, but we don't need to use it here. And if you think about conservation laws, there's one more conservation law that we can use. In the conservation of, yes, conservation of energy. Somebody was saying conservation of energy. And so what is the conservation of energy here? I can again go to Wikipedia and copy the conservation of energy from the Navier-Stokes equations, which is very complicated. But I can also just simply use the equation, the conservation of energy from first year thermodynamics. And for that, you don't need to remember a lot, because the only thing you need to remember is what is the D, and sorry, I'm using U again, so maybe I should use a E. Let's use a E. Did I use E somewhere else? No. So the change of internal energy of a system is the same as how much, so this is the total differential of the internal energy is equals the inexact differential of heat that is added across the system boundary and work, right? And then we know that we can use for dq, we can use exact differentials because the dq is nothing else than TdS, right? And what is the inexact differential for work in a closed system? It's, anybody still remembers? P d v. This is the first law of thermodynamics for a closed system. Now I can use the definition of enthalpy because we have the enthalpy here. We have the enthalpy here, so I can use the definition of enthalpy is E plus PV. And if I use the definition of enthalpy and do the derivative of the enthalpy, then I can get T ds equals, and I wait a bit for your answers. What is it? Plus d dP. And we made an assumption before already, right? So if we say that we have no boundary layers that we want to take into account here, and we also say that we have no shock waves, then the flow is isentropic. No viscosity, no shock waves, no combustion, no reaction, I mean, and no whatever and whatnot. And you can have, and it's also perfectly insulated. You have no heat losses across the system. Then the dq is 0 and TdS is 0. TdS is 0. Then we know that dH is equals 1 over rho dP. And now you can see that I got this here, and I could nicely replace now this equation. I plug this in here. I hope you see it. And what happens if I do that? I get an equation for total enthalpy dr is equals, I think it's C theta squared, right? There's no rho, plus C theta dC theta dr plus Cx dCx dr. And if you are very good in math, then you will be able to see that this is nothing else than C theta. Let me write it in black again. C theta divided by r d r C theta dr plus Cx dCx dr. And this is a very nice equation that now tells me several things. Let me check if I made a mistake here. No, I think it looks fine. Yes, right? Otherwise I would see also some messages here. I think it's correct. So I see here that the change of total enthalpy from blade root, from the root of the blade to the tip of the blade, is basically a function of these two terms, right? So you can see that if I want to have a change in total enthalpy across the radius, then I know, because of this equation, that because of my Euler equation, I know that C theta has to change, right? Or U has to change. So these kind of things. If I change the enthalpy using my Euler equation, I know that U C theta has to change, right? Which means that automatically I will also have a change in axial velocity, right? So I might have a stage that looks, I might have something like that. So I have a shaft, and on top of the shaft I have a rotor blade and a stator blade, right? I have the casing, the outer casing, and I have here the stator for a compressor. This is now a compressor, and this is the shaft, and it has a certain rotational speed. So now you can see that the axial velocity, most of the time I would like to keep the axial velocity constant, right? So if this is the profile of the axial velocity as a constant, I know that this guy is going to be 0. And most of the time also I can already say that in my design I would also like to have a constant total enthalpy across the radius, so also constant. Then I can say that this term has to be 0. Let's say this is one design that I can choose. Of course, I don't need to choose for constant enthalpy across the radius, and it's in fact not always done. And you can optimize it for efficiency. Maybe if you optimize for efficiency, you will see that actually the enthalpy will have to change. And but as a first guide, let's say I say that I will have an axial velocity profile. So the velocity is constant across the radius. The axial velocity is constant across the radius, then this is 0. This guy is 0. And enthalpy is 0 across the enthalpy change. The enthalpy change across the radius is 0. And then you can see that this term has to be 0. And this term to be 0 means that dc theta r drc theta dr is equal 0. Or in other terms, r c theta be constant. And also, again, in AFD, you are discussing this, or you have discussed it already, I don't know, is that if c theta is equals a constant divided by the radius, it's called an irrotational vortex, right? Or vortex-free design. This thing will be called vortex-free design. With a vortex-free design, you have ensured constant axial velocity across the radius and constant total enthalpy across the radius. And then you know that you have to vary your c theta as a function of a constant divided by r, which is a hyperbola, right? So your cr or c theta has to change as a function of a hyperbola. Let me put it here. It has to be a function, something like that. This is now my c theta. Okay. This is the tangential velocity. I'm plotting it now as it looks like it's an axial velocity, but imagine that these velocity arrows are actually in this plane. So it's normal to the plane here that I'm drawing, and it's c theta. And so you can see that c theta is a function of constant divided by r, it's a hyperbola. And why is this called irrotational vortex? Because you have a flow, right? So if you look at from the front, if you look at it from the front, then you have a, now I'm plotting it again. Let's say this is a c theta profile. So this is the c theta. And that c theta now has this distribution as a function of radius. But if you put a tennis ball here, and the tennis ball, you paint on it an arrow, and the arrow points up. If you put the tennis ball inside this flow, the tennis ball will just move around this way, but the arrow will always be pointing up. The tennis ball itself is not rotating, and that's why it's called an irrotational vortex or free vortex design. Okay? And now let me go back to the slides. And then I finish this and I discuss the homework assignment. So all of these things that I discussed now are also given in the slides. And I did it a bit slower. And you can see here that, of course, you can also define, you can also use the definition of vorticity, right, which is nabla cross C. And if you say the vorticity should be 0, you will also end up with the same relation here, RC theta is constant. But now if you want to design a machine, and you can see this here, is you know that at the inlet, you have a certain distribution of C theta. Maybe C theta is 0 because the flow in the inlet of the compressor stage is purely axial, right? But at the outlet, you have a distribution of C theta. And that distribution of C theta is now a function of these guys here. So you're designing at midspan. In the middle, this is the midspan. At the middle, I get a C theta. And that C theta is, I have designed it at the midplane. And now I know how the C theta has to change as a function of the radius towards the hub. This is the hub, and this is the shroud. By just simply keeping this relation in mind, I calculate A2 as R midspan C theta 2 at midspan. And then I can calculate, of course, the other C theta. And if I do that, you will see that I will be able actually to calculate also a variation of alpha 1 as a function of R, and a variation of beta 1 as a function of R, alpha 2 as a function of R, beta 2 as a function of R. And this is nothing else than A1 divided by R here, divided by Cx. And Cx, we said, it's constant across the whole stage. Then you know alpha 1 will change this way, beta 1, and so on and so forth. So just simply using this design guideline, right? Now you can see that how does it look for a typical compressor stage? You can see the nice thing now, you can see that this here is the radius, R over R tip radius, so it's 1, because tip radius is, of course, the maximum radius. If I define R, if I normalize the radius by the tip radius, I get 1 here, right? And then you see that I can also calculate how alpha 1 will change. This is alpha 1. This is alpha 2. This is beta 1 and beta 2. And then you can also see other things here, for example, the Mach number. This is the Mach number for the stator and for the rotor. And the Mach number here is 0.5, and here it goes to 0.9. So for the rotor, you can see that close to the tip of the rotor blade, right? This is the rotor. This is the tip. Close to the tip, you will have very high Mach numbers. Of course, because the radius increases, the blade speed increases, and you can see that the blade Mach number goes up. And you would like to keep the blade Mach number close below 1, otherwise you get shock waves here. And so now you can say, okay, I don't want to use this design that I say the total enthalpy stays constant, but I want to use a different design such that I can have Mach number that will not be 1 or close to 1, and then you can change this and you can come up with different design rules. And this I keep it on the slide. But given the time, because I also need to leave a bit earlier, I will go through this a bit faster now. But this is basically it. So I discuss it until here. So you can have different design rules, but the design that we are going to discuss for the homework assignment is a free vortex design. Okay. And now let me open. With this, I would like to finish these slides and these lectures that are related to the lectures that I'm giving actually in turbomachinery, because now Sika Klein is going to take over on Friday, and he will discuss also hydraulic machines. But now I would like to discuss with you the homework assignment, which is given here. And you can see that in this homework assignment deadline, I put it here, Tuesday, December 8, 2020. Send the assignment to me. Also the first assignment, please send it to me. If you have questions, also send me an email. Don't send an email to gustavo.otero@tudelft.nl. He's not here anymore, but he was on the old slides, okay? And the assignment is like this. So you have a blade design, and now it's for turbine. So you need to do the same thing for a turbine. The stuff that I just did for the compressor, you need to do it as a homework assignment for the turbine. And you design the three-dimensional shape of the stator and the rotor for turbine by assuming that we are going to use the free vortex design. These are the conditions that are given here, right? The power output of that stage, we are operating with a gas constant of 287 and a kappa of 1.3. Mass flow rate is given. The total conditions at the inlet are given. Shaft speed is given. And the hub radius at the inlet is 30 centimeter, which is this one here. Right, this guy here is 30 centimeter. Assume that the velocity is constant across the whole stage and it has a value of 150 meter per second. With that, you can already calculate the mass flow, or given the mass flow, you can calculate the density and whatever and whatnot. Also the area, I mean, you can calculate the area actually. How high does this need to be in order to satisfy the mass flow? And then what you need to do for the homework assignment is you need to design the blade at midspan, of course. And then you calculate the area, 1, 2, and 3. So this is, what is the area at point 1, what is the area at point 2, and the area at point 3, if you assume that Cx is constant. The density will not be constant, and that's the reason why the area has to increase, because you're expanding the flow. Static pressure across the stage, then the three-dimensional, and this is the part that we discussed today. So you need to design a 3D stage. You need to design how the angles change for the stator and for the rotor, and then plot the radial distribution of the loading factor. Now, how does the loading factor change as a function of R? Flow coefficient, degree of reaction. These are the things that you can calculate. There's a question, is it indeed 30 centimeter? What is that? Yes, this is, the inner radius is this part here, let's say, and that is 30 centimeters. Okay. Then you can also approximate 3D design. If you want to design it in 3D, you can also do it. You can have a 3D design with the design software, AutoCAD or SolidWorks or whatever. So this is a bonus point. Deliver report around 4 pages, group of 2 students, just like before. Are there any questions? The homework assignment, I will make them available today on Brightspace. If they are not already available, I think, Luke, you can also make them available on Brightspace. Change the date. I will change the date and then upload this version of the homework assignment. Then for the people outside TU Delft, also these presentations will be uploaded on Google Drive. And I think that's it. I would like to thank you. Does each student in the group have to mail the report individually? No, this question has been asked also for the first homework assignment. Just send one homework assignment to me and just put both names there. Okay. Any other questions? if there are no other questions now, then of course don't hesitate to send me an email, and I will reply to your questions. And with that, I would like to thank you. And then Friday is the next lecture, Friday morning with the Sike Klein. I think he will discuss the hydraulic machines. Thank you so much. Bye-bye.
Thank you. Bye.
Bye.